you. So I want to say that I've written notes, a typewritten, 30 pages. On, it's not perfect, there's a lot of mistakes and so, but maybe it can be useful. So Giuseppe and Yoshi will send the notes to all participants. Okay? So if you find mistakes, you just tell me. It's not just for this concept. Okay? So that's the first one. The second point is that today, I apologize, but it will be really elementary. So, yesterday, I divided my talk in two parts. Real, so real manifold, and then you have F a shift on the sense of Dirac category. Then you associate its microsupport, singular support, which is a set. Okay? And when X is a complex manifold and the coherent D module, then you associate its characteristic variety in the cotangent bundle. Okay? So now we want to do more. We want to construct, not only these are sets, nothing more. So we want to construct something more mathematical, like module or categories or various things associated to the cotangent bundle. Okay? So the situation is much easier, so complex is much easier, because there is a Schiffer-Frey, dx, which is a basic object, and there is nothing similar, or of course there is a constant shift, but it does not play the same role. And as I answered to some question yesterday, if you take real differential operators and the real manifold, it's not interesting. Yesterday I explained why. Okay, so today I start with the complex situation. Okay, and if I have time, I will explain what means macrolocalization. So the end now is very vague, what means macrolocalization. So I do that first in the complex domain. So if you remember, if if you have a V complex vector space, finite dimensional of course, and if X is open, you can, and if you have a differential operator P, you write it like that. But you can take the total symbol, what is called sigma so to speak, which is just a polynomial. The same thing, but you replace the derivation by xi over. Okay? And it is a natural question, which comes from PDE in particular. Sometimes we want to invert P. For example, I take just a very easy example. Take Rn in Cn, and you take the Laplace operator. Then if the total symbol of plus, okay, let's say, of is this polynomial. Okay? But xi is complex, huh? Complex coordinate. And it's well known if xi is obvious, not well known, it's well obvious if xi is real, then this is invertible. One says the operator Laplacian is elliptic. So it's natural to try to invert this operator in the neighborhood of the conormal bundle to Rn in Cn. Okay? So if we want to invert then we cannot remain with polynomial, we need a series. So first I work first in this setting. X is the affine setting. X is affine, is open in some complex vector space. Okay? And I take series, so let's call S, maybe, S, T star X, maybe with a hat because it will be formal, is a set of formal series from minus infinity to some m of PGX psi, where PJ is holomorphic, of course. So in some open set, let's say U, so U is open in T star X, PJ is holomorphic in U, and also homogeneous of degree G. Okay. So J, in French, G and J is very difficult. J. And of course, if you are defined in the neighborhood of the zero section, then it will be a polynomial. Okay, but it generalizes the notion of polynomial operator, and we define a product So you remember the Leibniz product for differential operators. We take the same formula, but we extend it to this case. So we define f star g at x psi as a series for alpha in n power n, 1 over factorial alpha, g alpha psi f, g alpha x g. So it's the same formula, I suppose, as yesterday. And so we have now a non-commutative sheaf of algebra. Non-commutative sheaf of C algebra. And here you can invert. So now assume that f has order m, let's say, and the symbol of order m of f is invertible. What is the problem? Ah, okay. So let's call this G equal. So you can take G minus 1 star F. It will be something like 1 plus A or minus A, where A has order strictly negative. And if you want to invert, then the invert of this 1 minus A minus 1 is a series, as you know, A over n for the star product. Okay. So we have succeed in inverting operator with symbol does not vanish. But this is local, in a local card. So there is a theorem by Sato Kashiwara Kawai in 1973, published in 1973, they have done it before, which says that for any, if X is a complex, so now it's no more local, a complex manifold, then there exists So there is a filtration by the order. So there exists a filtered sheaf of C algebra that we call E T star X. It's not the same notation as Sato, but never mind. Such that the graded, so it's filtered. So if you take the graded ring, you find the direct sum of O T star X J. You have a monomorphism if you of differential operators that you take back, so it's a shift on the cotangent bundle. I recall that the projection is called phi. The inverse image of D is embedded in this new shift, so there is a hat. Sometimes I forget it, but there is a hat, I will explain why. On the second condition, when X is affine, then the total symbol, there is this total symbol map, which is an isomorphism from E X to the sheaf of symbol. Okay. So in fact, it's not at all the way Sato and his collaborator constructed this. They constructed functorially with a, it's very, very difficult with the macrolocalization functor and so on, but in particular, this implies this result. So it's an isomorphism of algebra, of course. Here, the product, the star product. Okay, so you know what is a macrodifferential operator. In a local cart, it's a series from minus infinity to some m of homogeneous symbols.
You mean T star X or?
Oh yeah, excuse me.
This is the same.
Okay. So if we use so again, it's very similar to differential operators. 1, 2, 3. Again, if we use, so this ring is not commutative. So as I said yesterday, it was a very big psychological barrier for the people until the 70s. Something non-commutative, they didn't want to hear about that. But it's almost commutative because it's filtered and the graded ring is commutative. So you can apply all tools of algebraic geometry, and in particular you find corollary that this ring is right and left coherent. It's very important, of course, on many of the results. So now I give, so we can speak of, since it is coherent, we can speak of system of macrodifferential equations that is M a coherent, so I mean left, huh? When I don't say anything, it means left. A coherent E module. Then it has a theorem. There is a theorem. Yeah, maybe we can define support of n in T star x, but in fact it's easy to see that this is also the support of O T star x transfer graph E T star x graph n. Assume that n has a filtration. I don't say exactly what it means. A good filtration. So you take the graded ring, the graded module, and tensorize, then it's a O T star x coherent module. It has a support, and it is the same as the support of n. So there is a theorem, again by Sato, Kawai, Kashiwara, of the same time, which says that the support of M, which is also, that's a notation, also called the characteristic variety of M, is a closed conic for the sister action, complex analytic subset. So all these things are obvious, but what is not obvious is that the characteristic variety of M is co-isotropic. And this is due to Sato Kawakashibara, as I said yesterday. And the link with D module is as follows. So, T star X is flat over pi minus 1 dx, which means that this functor, the tensor product, is exact. This functor is exact. And moreover, if you have a D module, if M is a coherent D module, then the characteristic variety of M is also the characteristic variety of the E module associated with M. So this is a very nice ring, okay? So maybe I will not develop this point, okay? I will pass to DQ module very soon. But before passing to DQ module, I want to make two remarks, okay? So the first remark is that there is a subring of this one. So what I have described, in fact, is a ring of four-man macro-differential operator. And more interesting for analysis is this ring where, by definition, you take the symbol, so it's local, okay? So this is a set of P, so that the total symbol of P is, as Misha said, Borel summable on each compact. So it means that if you take the series, let's say smaller than 0, of P, J, X, psi, and you divide by factorial J, this is less than infinity on each compact set. Not very good. Okay. So this is a subalgebra, which is when you construct cohomological things, starting with the holomorphic function, you arrive to this ring, not to this one. So this one is a little artificial, but for practice, in practice, of course, it's easier. But there are situations where it's necessary. Okay, so before to pass to DQ module, I want to, so remember, on T star X, here I work only with homogeneous things, sheaves, okay? So in fact, T star X is a symplectic manifold with a two-form omega X, but it's better, I don't know the name, homogeneous symplectic, there is another name, I forgot, with a one form, the Liouville form, alpha X, so in coordinate it's sigma d psi j dxj, and in local coordinates, sigma psi j dxj. Okay? And in fact, we use the homogeneous symplectic structure. Okay? So, if we work on T star X outside the zero section, and if I divide by the C star action, I find the projective cotangent bundle. And essentially, we have constructed, at this time by Sato it was the projective space, we have constructed a sheaf on the projective space. And this space is a contact manifold. Then, so it's just a remark, a second remark. Then comes a question. Now, if Y is a complex contact manifold, then locally, there exists B, which is isomorphic as a contact manifold to an open subset of some cotangent bundle. So here you have the sheaf or formal, let's say formal, E is star X. So a natural question is, does there exist a sheaf on Y which is locally isomorphic to the sheaf of macrodifferential operators? So question, does there exist on unique or canonic Calais some E Y, or formal or not formal? Okay. So the answer is yes, with a quote. So it's due to Kachiwara in 96, but I could quote because it's no more a sheaf, it's a generalization of sheaf. It's called a algebraic stack. So locally it is a sheaf, but when you glue, you have to take a higher order per cycle. So it's an algebraic stack, a notion which was introduced by Maxime 5 years later, or 4 years later. So this was not, but what was constructed by Kachiwara is the stack. Stack means, roughly speaking, a sheaf of categories. So we constructed the stack of modules over this non-existing ring. Okay, so now, so until now we have worked on contact manifold, but for some reason, homogeneous symplectic structure. But sometimes people want to work they want to forget the homogeneity. Okay. So, how to pass to non-conic? You have some situation where everything is conic, and you are tagged with the C plus C star action, and you want to to get rid of the C star action. So there is a very classical trick, which is to have the variable. So I call H bar a formal parameter. I think it's not a good idea to call it H bar, but instead of taking homogeneous series of homogeneous function, I will write U equal H bar psi, and then I can write this as G from minus n to plus infinity. Maybe I change my notation. H bar J J of X U. But now this is no more homogeneous. All the homogeneity has been put in H bar. So, and we define a star product similarly. Where is it written? It's not written in my notes. So I skip it. Now it's written.
It's the same formula.
Yeah, there is H bar. So now F X U star G X U will be sum for alpha in N power n. So now you have h bar over alpha over factorial alpha, d alpha u f, d alpha, no, d, x, g. And in fact, there is an intrinsic construction. So I find like that a new sheaf of algebra that I call W. So W hat, because it's formal again, this are X. So a sheaf of, so now the base length is no more C, is C H bar, Laurent series with respect to H bar, and with this product.
But are you still on the potential number?
Yeah. I'm still on it. I will pass to general Poisson manifold later. Okay? And I have pi minus 1 dx goes to E chapeau x, T star x, excuse me, W, T star x. And it's interesting to notice H bar. You can construct this intrinsically starting with macro-differential operators by adding a variable. So take the ring E on T star x cross T star C, but take the differential operators which do not depend on T. T hat means there is no T. So the symbols are series of PG, X, psi, tau. And you put H bar equal to minus 1. So this is defined on T star X plus C and tau different from 0. And you take the map to T star X, X, psi, X, T, psi, tau gives X, psi over tau. Then this ring W hat is nothing but the direct image of the sheaf of macro-differential operator on X plus C, not depending on T. So you see H bar here with this construction is more or less the Fourier transform or the inverse of the Fourier transform of T. Of course, this has no meaning. Huh? It's not a precise meaning. Okay, but now that we have this formula, we can ask the question. Of course, what I say is not historically true. Huh? Historically, things were totally different. But now we can put things in this order and start with this formula or something like that. And it's a theory of DQ modules that Jan used this morning and that I will explain now. Okay. So you can forget everything. Till now, I erase and I start from the start. So DQ is for deformation quantization. So you start. So Y is a complex manifold. So you can think, but you are not obliged, to this star X. But in fact, it will be much more general. So definition. So I will work, excuse me, with a ring OX with formal series in H bar. So a section here is a series from from 0 to plus infinity, fj, x, what is my x, h bar, y, exactly. Thank you. So I don't give a name to the variable. So it's a formal series of holomorphic function. It means that an open set is a formal set. On the star product, so I have to take care because there are a lot of very good specialists of star product in this room. So a star product is a bilinear C H bar bilinear. So the important word is associative. Multiplication law. And OY star. With some property, it's so that F star G is a series, can be written I positive of Pi F G H bar over G, where Pi is a bi-differential operator on, with some condition. P0 F G is a product. P1 F1 equal P1 1F equals 0.
All the PIs. Not only P1.
Yeah, yeah. Okay, so I should mention that this definition, due to so many people, one paper by B, F, L, S, by Flato, from Star, Lishnerovich, and Sternheim, okay, in 78. That's the definition of a star product. And when you have a star product, you have a Poisson structure, which is, you can define the Poisson bracket, you define the bracket Fg, which is H bar minus 1, the bracket, usual bracket for the star product, F star G minus G star F, modulo H bar. So when I start with a complex manifold, if I have a star product, in fact, my manifold has a Poisson structure, okay? But not necessarily symplectic. Okay? So what is a star algebra? So it's a DQ algebra, or a star algebra, you know. So a DQ algebra, A and Y, is a C star algebra, le carré isomorphic to O, Y, H bar, star, for some star product. Okay. So this is interesting because, for many reasons, but in particular you can notice that it can be commutative. So if it's commutative, H bar is just a formal parameter and it's classical analytic geometry. Or it can be symplectic, the Poisson structure associated to it. If it is symplectic, then look at it. It is the algebra. If Y is symplectic, then locally, A is isomorphic to the macrodifferential, formal macrodifferential operator of order 0, because it's H bar is not, I've not inverted H bar. Okay. Okay. And you have a principal symbol map. So now, I hope it's clear. You are allowed to ask questions.
When you say algebra, it's really algebra? That's
No, I have defined a DQ algebra. In practice, one needs more. Okay? One needs the algebraic stack. But I don't want to enter this subject. I've not said that they exist. Huh? So maybe I can say it now, if you want. If y is a complex Poisson manifold, then the question is, does there exist on how many class of isomorphisms A, Y, such as the associated Poisson structure is that of Y. So the answer again is yes, with code, and this is due to Koncevich. So it's yes without code in the real setting, and real manifold. Because all what I've said, you can do the same for real manifold, but on a complex manifold, you have to replace again sheaf of algebra by algebraic stack, which is a difficult, which is a very boring, and I will not explain what is an algebraic stack. But locally, so it's yes, locally. Without code. Okay? Okay, and we can, so now we play the same game as for macrodifferential operator. We have a symbol map, or sigma 0, from A to A over H bar A, which is canonically isomorphic to OY. So if we have a, so A is filtered by H bar J A, containing H bar J minus 1 A, H bar A. So we take the other, and we can prove by this that theorem A is right and left coherent. So we can speak, since the ring is coherent, we can speak of a system of linear equations in this ring that is A module. Okay. So we have the notion of a coherent module. So we have the notion of coherent A module. So it's a notion which generalizes both coherent macrodifferential operators or coherent O module in the commutative case. Okay. And we need, but the problem now we have H bar, and we can have H bar torsion, as we have seen this morning. So we localize, so we denote by A loc. This is A tensorized over C over the formal series in H bar of C H bar. So the meromorphic, so we invert H bar, okay? So now a symbol will be some from j equal minus n to plus infinity mj h bar over j. Okay, so we allow j to be negative. Okay? So there is no more h bar torsion, okay, because we are in a field. There is a theorem now. Again, it's coherent. So M est cohérent A log module, or equivalent. It's true also if M is a coherent A module with no H bar torsion. It's similar. Then the support of, excuse me, I forgot. No? Yeah, maybe I assume, I don't know if we are right. Okay, now I assume, excuse me, I forget. I assume, now assume that Y is symplectic. I don't remember, or I don't know, or I don't remember if it makes sense in the general case to be co-isotropic on a, it makes sense to be co-isotropic on a Poisson manifold, but is it true? I don't know. So anyway, assume it's symplectic, then the support of M is co-isotropic. Okay. So in particular, it's a complex, of course it's a complex analytic set. Okay, so now we assume that, okay, from now I will assume that Y is complex symplectic. Okay. So if M, I recall, is a coherent A, Y module, then the support of M is a complex analytic variety and is co-isotropic. Okay? So the proof this time we use Gaber's theorem. This moment, so if you have, when you are co-isotropic, as I said yesterday, it's natural to look at the extreme case where it's Lagrangian. Okay? So we say that M is holonomic if the support of M is Lagrangian. Okay, so it's very similar to the discussion of this morning. There is a theorem. So, yeah, I should mention that. So the main result on the existence of quantization is due to Maxime, as I said, but with Schapira, we have developed I forget, not important. We have developed the theory of DQ modules, and in particular, holonomic DQ module, and we have put the theorem if M and N are holonomic A log module, then R of over A log N is constructible, but over the field C H bar. on even better. So if they are holonomic in degree 0, that is not object of the Dirac category but real module, then it's constructible, it's even perverse. And there is another result, the dual, we up to a shift, the dual over, of course, over the, as a constructible shift of this thing is R of n with some shift that I forgot. Okay. So it's autodual. So we have a nice category of perverse shift, complex symplectic manifold, and among. So maybe I will make a link with a very particular case of what Maxime has said this morning. Now I assume that lambda is smooth Lagrangian in one. Smooth Lagrangian submanifold. Then I define L, I will say that L is simple, so L is a holonomic a log module. So I will say that L is simple if locally there exists L0 in L, L0 coherent A module, such as the symbol of L0, that is L0 divided by H bar L0, is isomorphic to the O lambda, the shift of holomorphic function on lambda. Okay? So this is a very natural and important notion. I remember that long ago, maybe 5 years ago, I asked the question to Maxime, does there exist always simple module? And Maxime told me yes. And after 3 years later, I put a theorem with Daniel that up to a shift, not to a shift, but to a twist, it depends how you define A, but more or less it's square root of omega lambda. Then there exists simple shift, a simple volume along lambda. Then I say, Maxime, no, but you have to twist. And Maxime told me, of course you have to twist.
No, it was known before the first quantization in philosophies.
Yeah, okay. Anyway, so now that you have assumed you have L0, which is simple and lambda, then you can look at the functor R1 over A naught L0 dot, which goes to, let's say, dB holonomic but supported by lambda A log. And it's easy to see that we go to the category of local Dirac category, I don't know how to, of local system. And lambda. Local system is the Dirac sense. Okay? Shields and lambda with micro support is a zero section. And if I remember, it's more or less obvious, except if it's true, but I think it's true, that this is an equivalent. The smooth case.
Yeah, it's local systems coefficients in the...
Ah, yeah, it's over CH bar.
It was decided to take a kind of limit when each bar goes to 0.
No, there is no limit here.
So we can have another multiplication by each bar.
It's purely formal.
Ah, yeah.
No, I think it's true. I don't remember. I had this to my talk. After your talk, I think it would be good to speak of that. So I had no time to check.
It's a zero section of the tangent.
No, there is no, yeah. Okay, maybe that's a good point. Maybe let me say that. Okay. Now here, you know, we work on the symplectic manifold. And symplectic manifold, no more homogeneous. So it's very different from the cotangent bundle because there is no, even if Y is the cotangent bundle to X, even when Y is equal to star X, X, that is the zero section, the zero section is a Lagrangian among others. It has no special properties. Okay? There is not a Lagrangian which is better than the other. When you work on T star X with the one form, the Lubin form, then everything is conic, and the zero section plays a fundamental role. Okay? But if you are purely symplectic, then all Lagrangians are the same. That's why to formulate a Riemann-Hilbert problem in this case, it's a totally different problem from the classical. Don't you agree? Okay. So one word more. Sometimes, so we have defined, let's say, when X, when Y is symplectic, so we have A on A block, but sometimes when you're, in particular for the Schrödinger equation, when you want to solve equation like the Schrödinger equation, you are led to define star exponential. Star exponential. It means you have to define exponential of P over H bar, where P has order 0. That is P in A, not in error. Okay? So it's out, it does not fit in this construction. Okay? So there are many people, it's a big, many people interested in star exponential, especially Professor Maeda, I think. And with Giuseppe, we have constructed a sheaf of algebra, very big, invariant by quantized contact transformation, which contains this. Okay? But it's very uncotangent bundle. I don't remember. Okay, but it's not for this construction. The formal case doesn't work. We need the Borel summation. Okay, it's just a parenthesis. Okay, so I think now I have half an hour. How much time? Half an hour. To treat the real case. So it's totally, I can erase everything because the intersection with the complex case is almost empty. So next week, we will have a talk by Tsigan, maybe, which make a link between the real and the complex case, but me, personally, I don't see any link. So I will be very sketchy. So I come back to the real case, and real manifold. So I have the category of sheaf on N. And if F is a sheaf, I have the macro support. So now I can construct if U is contained, or U, A, any subset in T star N, I can localize the triangulated category by the relation. So I can take dB A, let's say, A of Kn is So this is a set of sheaves such as the macro support is contained in the closure.
A is conical.
No, no,
Sorry?
No.
A is not conical.
no, not this is. Maybe it's the equivalent to the conical. Not necessary for the definition. And I can define dB Km as a localization so what will be important? Okay. What will be important is one point. So we localize. So what does it mean? Maybe I take one point. What does it mean? F belongs to dB Km P. It means that F is in dB Km, but they are much more isomorphic. If you have a distinguished triangle, F prime, F double prime, and P does not belong to the macro support of F double prime, then F is isomorphic to F prime in dB Km P. Okay. So you work modulo sheaves with macro support does not intersect A. So it's a, so maybe we can look, maybe okay, maybe I will take U upon. Okay, so we can take a T star M U dB K M U. So it's a free stack, but it is not at all a stack. Not very far from being a stack. Okay? So because to be in the quadrant bundle, that's why there is a symplectic topology. Things are extremely rigid, and you cannot glue things, and something can be localized 0, and is not 0, and so on. Okay? So, but there is something, but I have no time to explain it, maybe. There is a functor that we call UR. So I will come back here later. So there is the functor UR. So it's a bifunctor from dB Km of cross dB Km to dB K T star M. And this functor is a variant, so it's introduced by, so here all these things are due to Joan and myself, and it's contained in our book of 90, but the functor UM is a slight variation on Sato's macrolocalization functor. So I will say a few words if I have time later on Sato's macrolocalization. Okay? Sato defined macrolocalization along a submanifold which goes from dB Km to dB K star N for N a closed submanifold, and UR is a macrolocalization along the diagonal. Where there's the projection, n cross n, Q1, Q2. So yesterday someone told me that I have not used the 6th operation, but now I use them. Okay, so I don't want to, I have no time to be more precise, but it's a very useful functor which goes from sheaf on M to sheaf on cotangent bundle. And it has the following properties. maybe it's better that I look at my notes. So it's a generalization of R1, because if you take the direct image of mu1, you find R1. Moreover, the support of mu1 if you take mu1 of the constant sheaf and some manifold, this is a topology supported by n. So it's a particular case of the preceding. The support of mu1 f g is contained in the singular support of f intersect singular support of g. And also, which is very useful, you have assumed f is R constructible. So M is real analytic. Or, in fact, F cohomologically constructible would be enough. But then you have a distinguished triangle, which we call Sato's distinguished triangle, which is the dual, you take the dual of F consort G. So maybe G prime F is R on Kn, the stupid dual, goes to R on F G. And here you have R, you take the projection, but outside the zero section of mu1 F G. So pi with a dot is a projection of the codondant bundle, or excuse me, I have M, and this means T star M minus the zero section. So with this, you can extend mu1 as a functor from dB kn u up plus dB kn u to dB kn u. So in some sense, mu1 is the internal hub of this, for this pre-stack. So I will give other properties of mu1, but this shows that, of course, it's, we are tended to take the associated stack to this pre-stack, or to fix Lagrangians of manifold. Okay. So, of course, this is closely related to Fukaya category, but Tamarkin mechanic, but it's not very clear. Okay, and I want to give another property of mu1 that I like very much. So now assume that F and G are M constructible. So we assume that M is real analytic, and from K is a field, for sure. Then we have, I've never defined the duality functor. So there are two dualities on M. D prime M, F is R on F Kn, on Dn, F is R on F omega M, where omega M is a duality complex. So most of the people call this Verdier duality, but Grothendieck plays an important role in this frontal. Okay. So I call it duality and stupid dual. But I could call duality dual a stupid dual. Okay. So there is a nice formula that if you take the dual in T star n of mu f g, then you find mu g f with antipodal map on some shift also. No, there is no antipodal. Maybe there is a mistake here. Only transformed by the inverse image of the dualism complex on A. But I'm not sure if there is antipodal or not. No, it shouldn't. So why this formula is interesting, to my opinion, because it's a, I saw it's an evidence for mirror duality. Because, you know, this is a kind of self-functor. Self-functor were introduced by Bondal-Kapanov long ago. It's something very natural. It's, you have a self-functor if on f, g, star equal isomorphic functorial to on g, s of f. Assuming that these are finite dimensional. Okay? So that's the definition of a self-functor. Okay? So it's well known, or it should be well known, that if you take the category of constructible sheaf, or even C constructible, there is no self-functor. Okay. Except if you fix the stratification, but that's another subject. So there is no self-functor, but if you work macrolocally, then there is a self-functor. So it shows that if you look at constructible sheaf from a macrolocal point of view, then it has a self-functor, and it goes to the sense of mirror symmetry. That is the category of constructible sheaves. If you look at them macrolocally, it's behaved better like the category of coherent sheaves. Okay? And there is also a nice formula for mu1. So, yeah, but I cannot say it because it's about Fourier transform, Fourier Sato. So maybe, okay. So I will say a few words. I go backwards, and I want to define better mu1. So I say mu1 is a particular case of mu n, and to define mu n, you have to define two things, mu n and Fourier Sato. This is a specialization. Okay, so it's a vast program, but it's just an overview, of course. Huh? And in the notes, it will be defined more precisely. So let's take n in n. Then there is a functor, mu n, which goes from sheaves on n to sheaves on the normal bundle. So this is the normal bundle. And I describe it intuitively, I don't give a precise definition. Okay. So this is done, this is due to SKK, yeah? Or maybe Sato, I don't know, maybe, yeah, maybe Sato because it defines the microlocalization, so let's say Sato. So, but it will be conic. So this means conic sheaves. So I take an open set, V, so maybe I explain what it is in the particular case where n is 1 point. Okay. So I take a conic open set mu in T with n. Okay, so I make a picture. So what is nu n of mu a, mu n of f? The section. So the coverage is an inductive limit. So it will be, I cannot, I'm obliged to take the coverage. And I don't give the definition, but I'm making, oh, this is n. I make a picture. You take small sets, V, which are tangent to U. Okay? Smaller and smaller, but still tangent. Tangent in the sense of with the normal code. Okay? So when you take this inductive limit, you have the section of F on U. And what is the...
If you do just real block, it will be... If you make real block, it will be...
yeah, but you want the zero section also. I want it on T and N, including the zero section. Okay. If you make the blow up, you lose the zero section. Okay, you can do that. Anyway, the good definition is not this one. There is a blow up by deformation en code normal. Okay, but it's take time. So I give a short. Okay, so when I have n, I have the normal bundle on the co-normal bundle. Okay. So I have two vector bundles, you add one to each other, and we go from one to the other by Fourier-Sato. But as usual, people like the normal bundle or the tangent space. The cotangent space is not very intuitive, but in practice it's much more useful. Okay, so we want to go to the cotangent bundle. So what is the Fourier-Sato transform? So you have a vector bundle. Let's change the notation. So it's a new notation. Star. So star. And here you have the set P, the set of x, y positive, and P prime, x, y negative. I forget the x. Yeah, let's go Tx, the variable P on T, y on T. Okay. So on Q1 and Q2, so the Fourier-Sato, if you have the conic sheaf E, conic means it's constant on the ray, then we define the Fourier-Sato define the Fourier transform as you can guess, you can guess more or less, proper direct image, derived of course. So you take the inverse image of F and you transfer it by the constant sheaf on P prime. There are other formula, of course it's derived. Okay. So CON, that Fourier-Sato is an equivalence of category between conic sheaf on E and conic sheaves on the dual bundle. So it's interesting historically because it's around 70 Sato. Because it's much before Fourier-Mukai. So now it looks very natural to, when you have a formula, to translate it for sheaves. Okay? But at this time, people use with Fourier transform for distribution, but to pass from function or distribution to sheaf, and not to have an isomorphism but an equivalence of category, was not so obvious at this time. Okay, so the macrolocalization, un of f is the Fourier-Sato of mu n of f. So, what does it look like? So it's not intuitive at all. So I explain. Maybe here you have the tangent space, normal bundle, and here the conormal bundle. So here I take n equal 1 point for short, for simplicity, to make picture. Okay. So the normal bundle is a set of half-ray issued from A. It's very intuitive. And the conormal bundle is a set of half space passing through A. Space of half right? And here the space of closed half spaces. So this is intuitive, this is not, but in practice or in physics, as everyone knows, the phase space is more important than the tangent space. The cotangent is more important than the tangent. So, so if n is here, what is mu n f? Maybe just at one point, x psi, where psi is the conormal n. So it will be the intersection, it will be the inductive limit, so it will be nj, it will be inductive limit of hj of r gamma. So maybe I make a picture of this picture. So there is psi, and I take this sector. So I take bigger, almost a half space, and I cut by a small dot. So you create a epsilon, intersect almost a half space. So it's not very intuitive, but it's Sato's definition. Okay, so what is important? So we have mu n, Fourier, mu n, and finally mu r, which is very, very useful. But maybe I will not say more today. No. Yeah. Maybe another property of mu r, last property. So let's go back to Fourier-Sato. You have an equivalence of category, dB conic n plus k e, dB n plus k extra. And in particular, from Fg is isomorphic to F Fourier G Fourier, because it's an equivalence of category, so it's fully effaced. Okay? It's true with R. Okay, but this is global. Okay? It cannot be local because we are not in the same space. But now assume n equal V, real vector space. Then T star n is V cross V star, and there is a symplectic isomorphic, not homogeneous symplectic, but symplectic with V star cross V. Okay. X, Y, then if F and G are conic on V, then there's the theorem that mu1 F G is isomorphic after this isomorphic to mu1 F R G hat. Okay, so I think mu1 has very nice property. And I stop here. Yeah, I think I have said enough. And tomorrow I will do something totally different. I will give a proof, a condensed proof, but a proof of the Riemann-Hilbert correspondence in the regular case. So it's another subject.